Okay, relations, functions, one-to-one, onto, composition, inverse, transformations. Well, these are all things that have to do with functions and relations. Basically, a relation is a comparison of any two things. We'll start with a set. Now, two parts of a relation are the domain and the range. The domain is the independent, or the input, or the x value. So in this case, the domain is going to be given to us by, let me just take this and make this a smaller number from the thing here. The domain is 2, 4, 6. 2, 4, 6. And that's it, right? Those are all the x's that I have. And then the range here is 3, 5, 8, 9. 3, 5, 8, 9. All right? And then the question you'll be asked is, is this relation a function? Yes or no? Well, when you look up here, if it's a function, like none of these x values are going to repeat. And you'll notice x value of 2 goes to 3 and 9. So this is a relation, not a function. Okay, this is just a plain old relation. And when something's not a relation, it is not one-to-one, and it is not onto. It has to be one-to-one. It has to be a function before it can be one-to-one. Okay? Now, a mapping. A mapping is basically it's the same kind of thing. You take things from the domain and map them onto the range. Okay? So, like if you take 1 for an input value, you'll get 4. So the domain here is just going to be 1, 2, 3, 4. And the range is 4, 2, 3. Now, this is, in fact, a function, okay, because there's no domain value used twice. Like, for every distinct value of the domain, there's only one way to go, okay? If you put 1 into this function, you're going to get a 4. You can't get, like, a 4 or a 2, okay? So, for every x, there is exactly one y. All right, so it is a function. Is it one-to-one? Now, one-to-one means for every y, there's exactly one x. And you'll notice here, 4 comes from 2 and 1. That part right there makes it not one-to-one. All right? Onto means every y value, every element in the range comes from somewhere in the domain. And when you look at this mapping here, I don't have some random number that doesn't have an arrow drawn to it. So this is, in fact, an onto function. Okay? We'll go into that in more detail when we did it during the year. Okay? A graph. The domain is going to be all the possible x values, and the range is all the y values. With a parabola like this one, these arrows go down, they go infinitely negative. They go down, 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 but they're also going all the way out to the right and all the way out to the left. It's just going to take them longer to get there. Well, the domain is going to be all real numbers, right? X is an element of the reals, any real number. Okay? If you want to write this in interval notation, it would be negative infinity to infinity with parentheses. Because you cannot include infinity. It's not a number. Okay? So it's just a concept. It means it doesn't have any limit. Range. Now range is a different story here. These y values are, looks like it's from like here and down to negative infinity, right? And that's way too small for me to see. So I'm just going to pick a number. It looks like it's about 6. Okay, so I am going to say, I can say it like this, y, such that y is an element of the reals, and y is less than or equal to 6. Okay, you can also just write y less than or equal to 6 if you like. Okay, and you can also write it like this, negative infinity, comma, 6 with a bracket. Those are all three the same thing. This first one I use is set notation. It's not as common. Well, the second one is probably the most common one we would use, okay? And then the third one is interval notation. Now, for an equation, we're talking about the domain and range. The domain is the x values that are okay, all right? And we're talking about real numbers here, so I can't have a negative under the radical. The other thing I can't have is I can't divide by 0. Remember we did this in one of the examples we did. So, what would give me a negative under the radical? Let's see, if x was 3, I would get 0. If I had x was 2, I would have a negative. So it's going to be anything less than 3. It's going to be a no-no. So x has to be greater than or equal to 3. Okay? Now if you want the range, remember the square root of x. It just kind of looks like that. Right? And this is actually shifted 3 to the right and up 2. So it goes from 2 up to infinity. So my y is greater than or equal to 2. Okay? And that is a one-to-one function. One-to-one function. Okay? One-to-one. It's not onto because it doesn't go onto all the y-axis. Right? It does not cover the whole axis. Oh, I didn't do that here. Ooh, this is a function, but it's neither one-to-one or onto. Sorry about that. Okay, there we go. All right, each element in domain corresponds to 1 in the range, passes the vertical line test, and no x's repeat. Okay, and that is one-to-one. No, that's a function. Oh, sorry, that's a function, right. Okay, I apologize. Yeah, we already talked about that. All right, function notation. All right, if f of x is x squared plus 3, then this is 2 squared plus 3, or 7. All right, g of negative 3, I put a negative 3 in for the g function, so it's negative 3 plus 3, square root of 0 is 0. H of t is 2t minus 4. That's pretty easy. Okay, operations, if I'm doing f plus g of 2, well, then I have to do f of 2 plus g of 2. F of 2 plus g of 2. Okay, which is 2 squared plus 3 plus the square root of 2 plus 3, which is the square root of 5. 4 and that's a 7 plus the square root of 5. There we go. Okay, subtraction is going to be f of x minus h of x. Okay, and f of x is going to be x squared plus 3. It might be useful to use parentheses here because, look, I'm going to have to distribute this negative. 2x minus 4 is going to give me, keep, change. I'm going to get x squared minus 2x plus 7. Multiplication is f of 3 times h of 3. All right, and then you do them separately, right? You got 3 squared plus 3, and then you're going to multiply that by 2 times 3 minus 4. Okay, so that's 6. That's going to be 2. This one here is going to be 9, and 3 is 12, or 24. Division. Be careful. You cannot divide by 0. If you're dividing by 0, this is undefined. So like h divided by g of 3 is undefined. G divided by h of 3 is okay. It's g of 3 divided by h of 3. And the reason why it's okay is because, well, g of 3 is square root of 3 plus 3. Oh, sorry. H over g of negative 3 would have been undefined. This is just going to be the square root of 6. And then h of 3 is just going to be 6 minus 4 is 2. Okay, plus 6 over 2. Now, composition of functions. F of g of 4, right? And when you see it written with a circle, and it's useful to kind of do f of g of 4 to write it like this. Okay? All right, so I have the f function, and I'm going to use a big parenthesis there, take the x out, and put g of 4 in its place. Okay, so I want to do g of 4 right in here. Okay? So then g of 4 is the square root of 4 plus 3 squared plus 3. So that's going to be 7. Square root of 7 squared is 7. 7 plus 3 is 10. Okay, g of h of x. All right, g of h of x. So I start here, I have a big square root, and this is parenthesis where the x was, and I put h of x in there. So 2x minus 4. So it's going to be the square root of 2x minus 1. Okay, and there's my answer. All right. One-to-one functions. We already kind of talked about it. Every value in the range corresponds to one value in the range, and it passes the horizontal line test. Okay? If you look back up at this example right here, this fails the horizontal line test. That's why that was not one-to-one. Onto functions, for every y in the range, there is some x in the domain, such that f of x equals y. And basically, when you're looking at a graph, it's going to cover the entire y-axis. Like all these values of y up in here, right, from 6 up to infinity, anything greater than 6 isn't going to, you can't map onto it, so it's not onto. Okay? Are the following one-to-one, onto, neither, or both? So let me look at these quickly. This one is both. Okay? Now this one is one-to-one. This one here, it's a function. Now, do any of the y's repeat? Yes. So it is not one-to-one. But it is onto, because I'm going on to 2, 5, and 2. There is some way to get to all those values. When you have a set of values like this, it's always, when I have a set of ordered pairs, it's always onto. When you look at this graph, it covers the entire y-axis, so it is definitely onto. It's a function because it passes the vertical line test, but look at this, it fails the horizontal line test right there, right? So it is not one-to-one. Again, this one is onto. Okay. Inverse, algebraically, you switch your x and y, you solve for y, you rewrite using the inverse notation. All right, well, and this one is really simple. When you have a set of ordered pairs, all you do is switch your x's and y's. 3, 1, 4, 2, right, and 9, 3. All right, for this one here, I'm going to rewrite it with a y, and then switch the x and y. So it's like x equals the square root of 3y plus 5. And then square both sides, I get x squared. Minus 5 equals 3y. So then I got y equals x squared minus 5 over 3. And I use the inverse notation. F negative 1 of x equals x squared minus 5 over 3. All right, for this, sketch the inverse. You're going to find points that are on there and then switch the x and y. So this is negative 1, 2, 3, 4, 5, comma 1. So now I go 1, comma, negative 5. So that goes to like down there. This one, negative 2, 2, go down 2, and then over 2, there's that point there. This one here was the point maybe 2, comma 6 maybe. So I'm going to have 6, comma 2. I go over 6 and then up 2, and then you can see that is the inverse, okay? That is the inverse. All right. To verify an inverse, you have to take the composition of functions. You verify that f of x, 3x minus 2 all over 4, and g of x, 4x plus 2 all over 3 are inverses. So the composition of functions has to equal x, okay? So let's try f of g of x first. Right? F of g of x is going to be 3, big parenthesis, minus 2 over 4, and I put in 4x plus 2 over 3. And then I simplify it. So I'm going to have 4x plus 2. Yeah, the 2's are going to cancel after that. So I'm going to have 4x plus 2 minus 2 over 4. And then those will cancel. And I get 4x over 4. And then the 4's cancel, and it does equal x. And it should work the other way as well. I'm going to leave that for you as an exercise, perhaps, to try g of f of x. So you're going to have big parenthesis, you're going to have 4, big parenthesis, plus 2, and that's all over 3. And you put 3x minus 2 in there over 4. And see that it will simplify to x. Okay? Transformational graphing. And you've got your 3 parent functions, x squared, the absolute value of x, and the square root of x. And you're going to take those and you're going to shift them. Now remember, if you're talking inside the parentheses, it's the opposite of the way it should go. So this is going to be a parabola. It's going to be x squared shifted 2 to the left, left 2, and up 3. So if I have my regular parent function, just like this, that's y equals x squared. So if I wanted to graph that, I would take my vertex here and I would shift it 2 to the left and up 3, and then have a parabola that looks like this. All right, and that is f of x. Okay. Here, my parent function is the square root of x. I'm going to go 4 to the right, and I'm going to go up 7. So I take this point right here, I take this regular 0, 0 that used to look like that, and I go 4 to the right, 4 units to the right, and up 7, and that is g of x. And that's how transformational graphing works. Okay? All right. Well, good luck. And I'll give you some practice questions to work on this tomorrow. Thanks. Bye.